Hello everyone. Okay, so we are on page 10, so follow along with me and make sure you're filling your notes out as we go. There's not going to be a lot on this front page though, because you guys are familiar with chemical formulas. You know that on the left we have our reactants, on the right we have our products. We understand that a subscript tells us how many atoms are in that molecule, and a coefficient tells us how many molecules we have. So, an example, CH4, there's 1 carbon and 4 hydrogens, and that's what we see here. 1, 2, 3, 4 hydrogens. And then O2, so there's 2 oxygens in this molecule, and then we have 2 of those molecules. So we understand these concepts. Now, in addition to subscripts and coefficients, we also have our states of matter, and then there's aqueous, aqueous, that means dissolved in water. G is gas, L is liquid, S is solid. It's important to note, though, that atoms and mass need to be conserved in chemical reactions. Yes, bonds are breaking, bonds are forming, but we're not gaining new atoms. So atoms aren't disappearing. So whatever number and amount of atoms we are starting with, we need to end with. So if we have 1 carbon atom, we need to end with 1 carbon atom. If we have 4 hydrogen atoms, we need to end with 4. 1, 2, 3, 4. If we have 4 oxygen atoms, then we need to end with 4 oxygen atoms. And look, here they are. 1, 2, 3, 4. So if we have the same number of atoms in the reactants as we do in the products, that means mass is also conserved. Atoms equate to mass. So if I take all of these reactants and I add them together, then that would be like the mass of my reactants, and that has to equal the mass of my products. Okay? So that's why it requires us to have these coefficients, to have a balanced chemical formula, because whatever atoms we start with, we have to end with. Okay, now, balancing chemical equations. I have a couple little tips and tricks that can really help you. The first one is start with the most complex. So this is a little trick or tip that I have when it comes to balancing equations. Okay. And my first one is start with the most complicated. Okay, start with the most complex. Now, when I look at these things, they all look quite interesting and complex, but this one looks the most complicated to me. So I'm going to go from here to balance the other chemicals, the other atoms. I'm going to start with the calcium. So right now we have 1 calcium, but over here we got 3 calciums. So I'm going to put a coefficient of 3. Maybe this will change later, but I'm going to start with 3 because that would be 3 calciums, and then I have 3 calciums over here. Okay. Now, what does that mean for the hydrogen? Because the hydrogen's only present right here as far as the products go, and then right there with the reactants. So I want you to think about this for a minute. There are 2 H2s in one of these compounds, or one of these molecules. So 2 times by 2 would be 4. So one of these has 4 hydrogens in it, but then there's 3 of those items that each have 4 hydrogens. Okay, so like, again, one of these things has 4 hydrogens in it, but there's 3 of them. So that means we are dealing with 12 hydrogens. Okay, so that's how many hydrogens we have on the product side. And right now we only have 3 hydrogens on the reactant side. 3, 6, 9, 12. Oh, so we need a coefficient of 4 right here. Because if you do 4 times by 3, then we get the 12 hydrogens. So now we've balanced that. Okay, and then this leads to my second tip or trick. Keep polyatomic ions together if possible. Okay, keep them together when you're balancing a chemical equation if possible. And here's what I mean. I could separate the phosphorus and the oxygen. Same thing here. I could separate the phosphorus and oxygen, but I see phosphate. I see PO4. And so instead of counting the phosphorus and the oxygen separately, it's actually a lot easier to think of phosphate as an entire unit. So like if I take 1 times by 2, so that means right here we have 2 phosphates in this molecule, in this actually ionic compound. And then here we have 4 times by the PO4, so there's 4 phosphates. Okay. When you have hydrogens in the front, that almost always means that it's an acid. So this is some kind, so phosphate, so phosphoric acid probably. And then when I add those together, 4, 5, 6, so I have 6 of these phosphates. Now let's see how many we have over here. So inside one of these compounds, we have 2 phosphates. Okay, so I have 2 phosphates. But there's 3 of those. So 2, 4, 6. Oh, 6 phosphates. So everything is balanced. We have a coefficient of 1, 4, and 3. Okay. Another tip or trick that I have that we didn't end up using is you can crisscross like subscripts for coefficients pretty often, especially when they have like uneven numbers, and so then you can crisscross them so they equal each other. That's another little trick or tip. Okay, on to the next page. So we have this diagram, we have a balanced chemical equation, and we gotta say like what is this gonna turn into. Okay, so let's draw this honestly. Like there's my box, this is gonna be my product. So like this is my reactant, this is the product. And my balanced chemical equation tells me if I take 1 N2 and 3 H2s. Okay, so I'm gonna come over here. So if I take 1 of the N2s and 3 of the H2s, that's gonna turn into 2 NH3s. So let's draw that. NH3, so there's 1 of the NH3s. Let me draw another one. So I took 1 N2 and 3 H2s and they turned into 2 NH3s. But that doesn't mean that these atoms just like stop existing. They don't pop out of existence. There's not enough of the H2 to keep reacting, so whatever they were there in the beginning, they're just going to be there in the end. Those are our excess reactant, by the way, the one that we have left over of. This is an excess reactant, and our H2 was our limiting reactant. This is what stopped the reaction. If we had more of the H2, we would have made more, but we only had enough of it for the reaction to happen one time. So let's see what we got. A is not the correct answer because it's missing the H2s. B isn't it, neither is C or D, but look, there's E. See how we have the 2 NH3s and then the N2s that were excess? So that's our correct answer. Okay, let's keep going. Write a balanced chemical equation for the dissociation of calcium hydroxide, OH-, calcium hydroxide in pure water. So it's going to dissociate, it's going to, dissolution, we're going to pull it apart. Like we are taking this CaOH2 solid, and we're going to put this in water. Now the reason why I'm not including the water is because the water is there in the beginning and the end. Let me show you. This is going to break apart. Okay, so we're going to take this, we're going to put it in water, and the water is going to break it apart so that we got Ca, and calcium is in group 2, so this is a 2+ ion, and it's dissolved in water now, so that would be aqueous. plus OH minus aqueous, but there was 2 of those, right? So when I break it apart, we get 2 of those. So this is what they're looking for if they ask for the balanced chemical equation for the dissolution of calcium hydroxide. Notice how we could have put like plus H2O here and plus H2O there, but the water would have been on both sides, so it just would have canceled. It's not actually part of the chemical reaction. And so this is our balanced chemical equation. Starting with the solid, putting it in water, and so then it pulled apart, and now it's aqueous because it was dissolved in water. Okay. You guys are really familiar with balanced chemical equations. Now we need to take it to the next step, where we are going to be doing ionic equations. Okay? So first thing, I need you to be able to identify when you have an ionic compound. And ionic compounds are metals and nonmetals and/or polyatomic ions. So we have sodium, which is a metal, and then hydroxide. And we need to know our polyatomic ions, and we also need to know what the charges of these atoms are based on their location. I'm going to grab a periodic table. Hold on. Slide on. Okay, so first thing. Anything in group 1, any atoms in group 1 form ions with +1 charge. Group 2 is +2 charge. We get all kinds of charges in between here. I have to tell you what it is in the name. And then we get a +3. So +1, +2, +3. There are 3 transition metals that you do need to know. The first one is aluminum. That one's easy enough because it's a +3. And then we're going to go diagonally to zinc. Zinc is a +2 and silver's a +1. So +3, +2, +1. Now to the other side. Noble gases don't form ions. Group 17 is a -1 charge for its ions. 16 is a -2, and 15 is a -3. We also need to know our polyatomic ions. So you need to know nitrate, sulfate, and phosphate. Okay, so these are our 8s. They all have those elements plus oxygen. And the number of letters tells us the amount of oxygen. So we have NO3, SO4, 1, 2, 3, 4, PO4. And the charge goes in order. So it's going to be a -1, or just a minus, a -2, and a -3. It's phosphate. Now, to go from 8 to 8 of any of these, nitrate, sulfate, phosphate, to nitrite, sulfite, phosphite, everything stays the same. You just remove 1 oxygen. So we got an NO2 with a -1 charge, an SO3 with a 2-, a PO4 with a 2-. Okay. In addition to this, I also need you to know carbonate, CO3 with a 2-, carbonate, and hydroxide, OH-, hydroxide. And then there's one more that we haven't talked about that I do think I need to add to this list, and that's ammonia, NH4+. It's really the only positive polyatomic ion that you're going to run into. Okay, so we need to know these. Great. Sodium is in group 1, so it's a +1. Hydroxide is a polyatomic ion. It's a -1. So I see a metal and a polyatomic ion. So this is an ionic compound and it's aqueous. That means it's dissolved in water. And any ionic compounds that are dissolved in water actually pull apart. So the Na plus will separate from the OH minus because the water will pull it apart. But first thing, we got 2 of each of those, and then it's dissolved in water, so we're going to go aqueous. Okay, so when you have an ionic compound, which is a metal and a nonmetal, or a metal and a polyatomic ion, or a polyatomic and a nonmetal, or polyatomic ion, then, and it says aqueous, then we separate them because it's dissolved in water and water pulls them apart. Okay, now here's a tricky one. Copper sulfate. Sulfate, SO4. Wait, let's see. Not some pigs. Okay, so that's a 2 minus. But do you see how there's only 1 sulfate? So the copper is in between here. Like, it doesn't tell us what the charge is, but since I see that it's with sulfate and it's 1 copper to 1 sulfate, then the copper must have been a 2 plus. So we get copper 2 plus aqueous, and that separates from sulfate SO4 2 minus aqueous. Okay, now that's our reactants. It's going to turn into sodium sulfate. So sodium, Na, but there's 2 of those, and this is aqueous again. So I need to separate it. So 2 Na plus aqueous and 1 sulfate. So plus a sulfate, SO4 aqueous 2 minus. Plus copper hydroxide, which is an ionic compound as well, a metal and a polyatomic ion, but it's solid. It's not dissolved in water. So when these ionic compounds are solid or liquid or gas, but I rarely see a gas, mostly see solids, sometimes liquids, but if it's a solid, a liquid or a gas, then we do not break it apart. In our complete ionic equation, it stays together. So it's going to stay together as CuOH2 solid. Okay. This is the complete ionic equation, where the ionic compounds, whenever they were aqueous, we broke them apart. Now remember up above how I told you, well, I'm not including the water because it would be H2O here and H2O here and they would cancel. That's what spectator ions are. Spectator ions are the ions that show up on both sides of the equation. So we have SO4 2 minus aqueous, and then it's right there again, SO4 2 minus aqueous. We got one other spectator ion, and that's sodium. We got 2 sodium ions, aqueous, and 2 sodium ions, aqueous. So Na plus is a spectator ion. It's just there spectating the chemical reaction. It's not actually part of the chemical reaction. And sulfate is the same way. So the net ionic equation removes the spectator ions. It essentially cancels the spectator ions. And whatever you're left with is the net ionic. So I'm going to take 2 hydroxide aqueous plus copper 2 plus aqueous. I don't do my spectator ions, and that turns into copper hydroxide solid. This is the net ionic equation that gets rid of the spectator ions. Okay, we're going to save this one for class. We're going to try this again together in class. And then I think this one as well, I think we're going to do this next one together in class. Okay. So, looking at actually example number 3. So, aqueous solution of iron 3 chloride. Oh, everyone, this is what I mean by I gotta tell you the charge in the name. Okay, so we have iron 3, and that doesn't mean necessarily that there's 3 irons. It means that the iron, which is a metal, is a 3+ charge, and we're going to be putting it with chlorine, because chloride, so it's just chlorine, it's not a polyatomic ion, and chlorine's in group 17, so it's a -1 charge. So when I crisscross those, the 3 would go to the chlorine, and the 1 would go to the iron. So it'd be like FeCl3. Okay, so an aqueous solution of iron 3 chloride and potassium hydroxide. Okay, potassium's in group 1, so it's going to be a +1. Hydroxide's a polyatomic ion, OH-. Oh, so it's just 1 to 1. So it would be 1 to 1, potassium hydroxide. Aqueous solutions. Oh, so they're both an aqueous solution. The iron chloride is, and the potassium hydroxide are mixed, forming iron 3 hydroxide precipitate. Okay, so we're going to mix these things. Are mixed to form iron 3 hydroxide precipitate. So when we crisscross the iron and the hydroxide, the 3 from the iron goes to the hydroxide, and the 1 from the hydroxide goes to the iron. But they say that it's a precipitate, and we know that's the formation of a solid. So this would be a solid. Okay, so it's going to turn into FeOH3 solid. Alrighty, but we're not done. Yeah, the writing stopped, but atoms can't just disappear. Like, the iron is there, sure, but where did the chlorine go? And what about the potassium? And those leftover things would come together. Like, if we take potassium, which is a +1, and we combine it with chlorine, which is a -1, then we get a potassium chloride. And because it didn't say directly in here, we can assume that these are dissolved in the water that we poured together. And so that's going to be aqueous. Okay. So is this balanced? Nope, it's not, because, and let's draw some lines in front of here to help us. Okay, start with the most complicated. Maybe this one's our most complicated. We got 1 iron and 1 iron, but notice how we have 3 of these hydroxides. So I need to put a coefficient of 3 here, so I have 3 of the hydroxides. And that means I'm going to have 3 potassiums, so I need to have 3 potassiums, which led to 3 chlorines and 3 chlorines. So these are going to be coefficients of 1. So we have 1 iron, 3 chlorine, 3 chlorine, 3 potassium, 3 potassium, 3 hydroxide, 3 hydroxide. Okay? What type of reaction is this? Okay, so what they like to call this one on the AP Chem test is a precipitate reaction. Because we took 2 liquid-looking things and we poured it together and we got a solid. Another name for this kind of reaction, not just a precipitate reaction, is double replacement. Notice how these switched partners, like iron was with chlorine and now iron is with hydroxide, and potassium was with hydroxide but now potassium is with chlorine. It's like square dancing, like switch partners. That's double replacement. Now we need to write the complete ionic equation. So all of these aqueous ionic compounds, we gotta separate those. Okay, I better write small. So I have 1 iron and it's a 3 plus aqueous plus 3 chlorine, and they're minus 1 because they're in group 17 aqueous. And then there's 3 potassiums, so 3 potassiums, they're in group 1, so they're a plus aqueous, plus 3 of the hydroxides, OH minus aqueous. So both of those were aqueous, so I separated those ions. Now product side. This one's solid, so I'm not going to break it apart. Remember, solid liquids and gases, we don't break apart in complete or net ionic. So this one's going to stay together as iron hydroxide solid. And then this one's aqueous, so I am going to break apart the potassium and the chlorine. So we got 3 potassium aqueous plus 3 chlorine aqueous. Great. Spectator ions, ones that show up on both sides. The chlorines and the potassiums. So Cl minus is a spectator ion, and potassium is a spectator ion. So the net ionic equation includes everything except for the spectator ions. So I have my iron 3 plus aqueous plus 3 hydroxide minus aqueous turns into iron 3 hydroxide solid. And that would be my net ionic equation. Okay, and then we got a couple concept checks, or really just this last one that we will do together in class, and then more stoichiometry next time. All right, everyone, fabulous work, and I will see you all in class. I look forward to hearing about your Thanksgiving breaks and how your break was. Okay, see ya.